Thanks for the introduction, and thanks organizer for giving me this opportunity to give this talk here. So today I will present something about the thermodynamic constraints on chemical reaction systems. So firstly is a brief introduction of myself. So currently I'm an Elbow postdoc fellow at Center of System Biology in Dresden, and also Max Planck Institute of PKS and CBG. So I'm broadly interested in non-equilibrium statistical physics. And more specifically, I study the chemical reaction system and the stochastic thermodynamics and also finite time thermodynamics. And in today's talk, I will focus on the first part of the chemical reaction theory. So the motivation of studying chemical reaction system is that we know the biochemical process, they are out of equilibrium. Like the pattern formation comes from reaction diffusion process, can form some pattern on the zebrafish and also on the intracellular level. This kind of pattern formation needs some energy injection to go from some uniform distribution to some spatial pattern to some organized state. And also living system need to do some information processing. You need to, for example, copy the DNA and also have a translation. It has a translation and transcription. And in this kind of copy process, the system need to discriminate different monomers. And to lower down the error rate, Hopfield proposed the kinetic proofreading scheme, which consume energy to go from the higher error rate to low error rate. And also living system, you run some circadian clock to keep track of the time. To run accurate time counting, it consume some energy, consume some ATP, and then dissipate some heat to the environment. And also in the intracellular level, living system need to actively transport different materials inside a cell. And this kind of motor protein will consume energy to have this kind of unidirectional motion. So the question is that what's the energy constraints on this process and how should we describe them? So to understand all this process, firstly, we need to write down the equation of motion of this process. There are two classes of this process. Like in the microscopic level, we have the master equation. We can describe everything as a stochastic Markov jump process. And so we have the master equation to describe the dynamics of all these systems. Like we will have a transition rate matrix and a probability distribution, and we describe a time evolution of the probability distributions. And over all the states, like for the proofreading, we have different binding states of the enzymes and the monomers. And for the molecular motor, we have the full all the discretized sites along the macrotube. And also we have something in a more macroscopic scale. We have the chemical reaction system, and we describe this equation by describing the time evolution of the concentrations. And this time evolution is described by the mass action law. For example, here we have some monomer bind to a dimer, and we can describe this process as a chemical reaction system. And now we have the equation of motion. What we want to introduce is the thermodynamics of the system. So we need to incorporate the thermodynamics with the kinetics. And to do so, we can introduce a local detail balance condition. Basically, it measures the irreversibility of the dynamics using the entropy production. For example, for Markov network, the master equation for any transition between two states, so we have forward rates and backward rates, and the ratio of these two rates is determined by the entropy production along the forward direction. So the more irreversible the process is, the more entropy production it produces from J to I, and the larger the ratio of the forward to backward rates we have. And we have the same expression for the chemical reaction system. Now here we have two monomer to bind to form a dimer, and we can have the forward reaction rate and the backward reaction rate. And the ratio of these two rates is also determined by the exponential of the entropy production rate divided by the unit Kb, the Boltzmann constant. So that we can define the thermodynamics on the level of the transitions. And when system is at thermodynamic, when there is no drawing force in the system is closed. It does not change the energy with the environment. It also does not change the matter with the environment. Then the transition rate only depends on the initial and the final state along the transition, the energies of the initial and final state along the transition. And so we have this kind of detail balance condition for the chemical reaction system, we have the same thing. We have the ratio of the rates, which is determined by the chemical potential difference of the substrate and the product. And if this kind of conditions, this kind of detail balance condition is satisfied, the system will finally relax to some equilibrium state. And in this equilibrium state, we don't have any net flux in the system. On all the edges, the forward flux will balance with the backward flux. And the final equilibrium solution, the stationary state of the system, should follow the Boltzmann distribution. Like for the master equation, we have the probability distribution can be given by the Boltzmann factor, proportional to a Boltzmann factor, and then after some proper normalization, we will get the actual probability distribution. And for chemical reaction system, we have the same thing, and the final equilibrium state will be the concentrations of the species will be determined by the chemical potential of the species. But when we drive a system out of equilibrium, for example, we can have some exchange of matter with the environment. Like here, we have some reaction can be coupled to ATP hydrolysis. And also for chemical reaction, we can also couple some reaction to the fuel to waste conversion. We consume some fuel molecule to drive some pathway. And then we'll have some additional terms on the transitions, on the driven transitions, which will be determined by the driving force along the transitions. So that means the system is driven from equilibrium, and the detail balance condition does not satisfy. So we only have this kind of local detail balance condition. The transition does not depend on the initial and final state of the states or the chemical species, but it also determined by some external driving force term. And what I show in the talk is that even when the system is driven away from equilibrium, so we have this kind of driving terms. So if we want to know the stationary state of a system, we need to solve the whole kinetics. But without knowing all the kinetics, we can find some bounds on the possible solution of the system. So it's like with the equation motion, describe the master equation or chemical reaction system. When system is closed, it can relax to a final equilibrium state. And this equilibrium solution is unique. When system is driven away from equilibrium, what will happen is that this energy injection will open a space in the whole phase space of system, and all possible solutions of a system should be inside this space opened by the energy injection. And all the stationary states must be inside the space. And also in this space, we can define some complex dynamics, which we cannot define on a single point for the equilibrium system. So, and this kind of space can be applied to different biological systems to get thermodynamic bounds on different biological functions. So the question I will answer is that what determines the boundary of the thermodynamic space, and how can we optimize the space, and how can we relate the size of a space to some specific biological functions? So, and to start with, let me describe a minimal out of equilibrium model. And from this model, we can already get some understanding, some very intuitive understanding of the thermodynamic space and the role of the kinetics. So here, it's just a two-level model. We have two different states. You can think it's the two different chemical species. We have two different pathways between these two species. One is spontaneous pathway, and the other one is driven pathway, which consumes some fuel molecule and convert the fuel molecule to waste molecule to push the system to a high ironing state. So you can understand this two-level system as a polymer folding process. The polymer can be in the unfolded and folded state. It can have some spontaneous folding pathway, and it can have another pathway which consumes some energy to make the folded state to unfold. Now, if we only consider a system with a single pathway, a spontaneous pathway, and we have the simple reaction schemes, and we can write down the mass action kinetics, and when a system can evolve to some final stationary state, some equilibrium state, and the equilibrium ratio of these two concentrations of these two states, or if you think it's a stochastic system, it can be the probability ratio, stationary state probability ratio of these two states, will be determined by these two rates. And according to the local detail balance condition, the ratio of these two rates will be given by the energy difference of these two states. And we define this factor as the equilibrium constant of this pathway. And now, if we only have a second pathway, we don't have the spontaneous pathway, we only have a driven pathway. We can still write down the mass action kinetics, and we can still get the equilibrium state solution of the system, because eventually, since there is only one pathway, the forward flux will balance with the backward flux. So we still have some pseudo equilibrium or equilibrium state, and the equilibrium ratio of these two concentrations will also be determined by the rates and the concentrations of fuel and waste molecule, so that we get a new equilibrium constant of this pathway, and which is determined by the energy difference of A and B, and also driving force provided by the fuel to waste conversion. So that means here we consume some fuel molecule to push the system from lower energy state to the higher energy state. Then we'll have higher probability or higher concentration in the high energy state. We will have more unfolded polymers. But now, if we only think individual pathways, we can get a stationary state, the equilibrium state. But what will happen if we combine them together? And in this case, these two different pathways will lead to different equilibrium states, and they will compete with each other because they are not these two equilibrium states are not they are not the same. So the final stationary states will be a consequence of the competition between these two pathways. And to know the exact stationary state, we need to solve the whole system. We need to know all the kinetics. But what I want to show that without knowing the detailed kinetics, without knowing which one is faster, we can still get some properties of the final solutions. That is, the stationary state ratio of these two concentrations will be upper bounded by one limiting case and lower bounded by the other limiting case. That's because basically the final stationary state it just comes from the competition between these two processes. It cannot go beyond these two limiting cases. And interestingly, the ratio of the upper and lower bound is determined by the non-equilibrium driving force. Like only when you have a non-equilibrium driving force, you have the fuel to weight conversion provide some energy to a system. This ratio will be different. So this ratio will be that's not equals to 1, and this upper and lower bound will be different. So if you don't provide any driving force, this upper and lower bound will be the same. That means these two pathways will lead to the same equilibrium state, and eventually the final stationary state is also the equilibrium state. We can also visualize it in the phase space of the system. The phase space is expanded by the concentration of the two species, and we have the final and we can plot one limiting case, which is given by one pathway. The ratio between these two states is a constant value, which is the equilibrium constant of this pathway, and the other limiting case, which determined by the equilibrium constant of the other pathway. And and with these two pathways, the system can finally relax to some stationary state, which is determined by the reactive look lines by solving the stationary state of the system. Because it's a linear system, the line will always have a straight line. And the intersection of the reactive look lines and the subconservation of the system, if the system have, for example, the concentration of A and B, the total concentration is a constant. And this intersection will give you a final stationary state solution. But no matter how we tune the kinetics, as long as the thermodynamic is fixed, and this reactive look lines must be inside this space, which we call the thermodynamic space. And by tuning the kinetics of a system, like we make the K, for example, if we make K, this reaction is much faster than this one, we can go approaching this boundary. And if this reaction is much faster than this one, we can go to the other boundary. But no matter how do we tune the kinetics, the solution will always be inside the space. And also the ratio of these two slopes will be given by the non-equilibrium driving force. If we don't have driving force, this boundary will collapse to the other boundary, and we don't have such a space allows us to move inside by tuning the kinetics. So this is just a very minimal model, and what I want to argue that I also will show in a mathematical rigorous way is this argument also holds for more complex and more general system, more general reaction networks. So now we consider some a network with many intermediate states, and we can pick up two states, the initial and final state I and J. And in a large network, we can still define from network topology, we can still define different pathways between these two states. And on a given pathway, we can evaluate the equilibrium constant along the pathway according to the which is defined as the product of the forward and to backward ratio on all the edges along the pathway. And this equilibrium constant, according to a local balance condition, it will be determined by the entropy production along the pathway, which is determined by which given by the energy difference between the initial and final state, and also driving force along the pathway. So for every pathway, we can find an equilibrium constant, which is related to its thermodynamic property. And this final stationary state should also be as a consequence of the computation of all possible pathways between these two states. And we can do the maximization and minimization over all the pathways and then we will find the same result, that the stationary state probability ratios of these two states, or we can also interpret them as the concentrations, the stationary state concentration of these two states, will be upper and lower bounded by the maximal and minimal equilibrium constant, which is maximized and minimized over all possible pathways between these two states. And if we think in a higher dimensional space, if we have a three-state system, has some conservation law, and we can draw the conservation law plan and the intersection of the thermodynamic space, and the conservation will give you a solution space of the system. And we system has thermodynamic equilibrium, so it only have one unique stationary state solution. And if we inject some energy to the system to make different pathways have different amount of dissipation, and then the driving force will open a space, and the solution will be inside this space. And also this more intuitive picture can also be proven in a mathematically rigorous way. We can do the matrix tree theorem. We expand the stationary state probability in terms of the spanning trees. Like we have a network when we can find all the spanning trees, and the stationary state can be represented by the sum of the product of the rates along all the spanning trees. And after some apply some inequalities to the spanning trees, we can get an upper and lower bound.
Sorry, can I interrupt 1 second on this slide? So, but
Yeah,
here
sure.
you consider networks, let's say, monomolecular, so like
Yes,
one
exactly.
species. Okay, yes.
Yes, here,
All
so
before. These are
this is
monomolecular.
unimolecular, but still it's not exactly unimolecular on the edges. We can have some autocatalytic reaction. So
Yeah. So it's okay, yes.
yeah, the backbone of the network is unimolecular, but we can, because it's nonlinear, by adding some autocatalytic reaction on the edges.
Yeah, okay. Yes.
So
Thanks.
that means this proof and this argument only holds for system, which can be represented by this kind of simple graph.
Yes.
But yeah, so this is the first result only for simple graph, and it can be proven using the matrix tree theorem. And in the next slide, I will show that this kind of argument also holds for more general chemical reaction system. So in a more general chemical reaction system, we don't have the unimolecular reactions. We can have this kind of dimer formation, like two monomer bind to dimer, and dimer plus monomer to a trimer, and the trimer goes to three monomers. And the first reaction in this example, we have the fuel to Bates conversion. So we can represent this kind of system using the hypergraph. Like we have a monomer, and we have this H which connect two monomers to a dimer and also convert a fuel to waste molecule, and this H which connect monomer to dimer to trimer, and this H we can say this H connect three nodes. So it's not a simple H as we have seen before. It's a hyper H, and the general chemical reaction system can be represented by this kind of hypergraph. But even in this kind of hypergraph system, the general chemical reaction system, we can still have a thermodynamic space, and we can still have the conservation law and the intersection of the thermodynamic space, and the conservation law will give you the possible solution space. How to do that? So here we introduce the techniques which is called the chemical probe. So in such a for example, if in this system we are interested in the stationary state ratio of the monomer, the dimer to a trimer, and we can add the fictitious reaction, which is we call the chemical probe. So which is a reaction does not exist in the original network, but it's allowed by the conservation law. It converts three dimers to one trimer to two trimers. And by adding this chemical probe, so we can do some hypercycle decomposition. We can find the reaction cycles in the network, which includes this probe. And so that we have two cycles, and if we go along the cycle, and there no if we go starting from here and go along cycle, the internal system will go back to this kind of monomer state, this dimer state. And then we can remove this probe so that what left in the original network with the decomposed cycle is a pathway which convert the dimer to a trimer, which is a pathway in the original network. And for different cycle decomposition, we can identify different pathways. And this kind of decomposition, if we only find the elementary flux modes, the elementary cycles in the system, this kind of decomposition, the number of decomposition is finite, so that we can find all the elementary pathways which convert one species to the other species. And along the pathway in the hypergraph, we can still define the equilibrium constant used according to a local detail balance condition. And what we'll find is that the stationary state ratio of the system, for example, here is the stationary state ratio of the dimer to the of a trimer to the dimer will be given by the minimal and maximal equilibrium constant over all the hyper pathways in the chemical reaction system. And we can do some numerical verification, like we have a system we keep the thermodynamics fixed. So we fix the chemical potentials of the states, and we also fix the driving force provided by the fuel to width conversion. And we can get a range of possible solutions for different pairs of chemical species, like dimer versus monomer versus dimer, and also some combination of chemical species. And we get a solution space, and the the green lines represent the system at thermodynamic equilibrium along the pathway which does not consume the fuel molecule. And we get an upper bound determined by the network topology and the drawing force, and which is the amplification bound of the system. So and also this is just one example, and in our paper you can find we have the proof of this approach for the most general system described by the mass action by the hypergraph. Yes, for any possible chemical reaction network described by a hypergraph, we can do the same thing and find the bound. So now I can go through some examples. The first one is a bistable system, a Schlögl model, which is basically an autocatalytic model. And we have a chemical species A, which can go to X. But this reaction is catalyzed by 2X, so it's a highly nonlinear reaction. If we think about this pathway, we have 2X, which catalyze the reaction to convert 1A to X. And if we only consider this reaction, the system will relax to some stationary equilibrium state, and the forward and backward flux on this edge will balance each other. And also we have another reaction, which is we can convert X to B. So we have another pathway. And the concentration of A and B, we keep them fixed, so they are chemostatic species. So that the system can this equilibrium distribution of X will be different from the equilibrium distribution of X of this reaction pathway, so that we get a lower bound and upper bound corresponds to these two pathways, of which will constrain the possible stationary state solution of the system. So this system is a bit more complex than the previous one I discussed. Here we can show some bistability, but no matter how nonlinear system is, the fixed points of the system will be bounded by the upper and lower bound determined by these two pathways. Does not depend on the kinetics, it only depends on the thermodynamics. And also we can draw the bifurcation diagram. We can show the bistability as a function of the drawing force. And on the intermediate drawing force, we can have some bistability. But no matter how small or how large the drawing force is, the solutions, the stationary state solution should be always inside the thermodynamic space we found before by comparing different pathways. And the second example is for kinetic proofreading. So living system need to do some copying process, need to do translation and transcription. And this kind of copying machines need to discriminate right and wrong monomers to add to the polymer chain. And this kind of discrimination, they can be achieved by this kind of simple binding process, like the enzymes can bind to right and wrong monomers and to form some complex, and then the complex will release a product. If the discrimination is achieved by this kind of this kind of simple process, the error rate will be determined by the energy difference of these two complex, and really these monomers, really these two monomers are not that different. So this kind of discrimination error rate will be too high. So Hopfield introduced the proofreading scheme which have one additional step. So here we consume some energy to push the system to a higher energy state, and then the system will release the product. It also can go back to the original state. So this is the proofreading step. So, and hopefully find that the error rate can be dramatically lowered down to the square of the original one, but in his original model, there is no thermodynamics. So what we can do is that using our pathway argument, we can identify all possible. The error rate will be defined by the stationary state probability ratio of these two states. And we can find all possible pathways between these two states and find the pseudo equilibrium states along these kind of pathways. So that the error rate will be lower bounded by this case. So we have a drawing force which push the system on the edge from the wrong state to the right state. We also have the upper bound, which we use energy in the wrong way to push the system from the right state to the wrong state. So we get our lower and upper bound of the error rate, and also we can fix the thermodynamics and randomize the kinetics to find that, okay, for randomized network, so the error rate cannot go below the lower bound, and also it cannot exceed the upper bound. And this exact result of the bound has been obtained before by optimization the solution of the system. But here we don't need to solve the system. We only need to find all the pathways and then identify the thermodynamic properties of the pathways. Additionally, in a more complex system, if we have more intermediate states, we can use the same approach to. So we don't need to do some optimization. We only need to find the pathways. We only need to do the topologies of network. And the final example is about the thermodynamic bounds on the pattern formation. So in a reaction diffusion system, so the nonlinear reaction and some unbalanced diffusion of different species can trigger some patterns in space, which is called the Turing pattern. So one feature in the pattern is that along the pattern, so the concentration of the species is not constant. So that it allows us to define one very good properties of a system, which is called the contrast or the visibility. Basically, the contrast is a range of the concentration of some species in the pattern, and which is properly normalized by the sum of the minimal and maximum concentration. Here we can see two different patterns, one with higher contrast and one with lower contrast. What we can use the thermodynamic space to show that this contrast should be upper bounded by the drawing force provided by the non-equilibrium process in the system. And here, the upper bound, for some specific example, the upper bound is in this form. And if we don't have an drawing force, and this upper bound will go to 0, that means without an drawing force, we don't have any contrast. So we cannot have a range of concentrations so that we don't have any actual pattern. And also we can do some numerical verifications so that we can see the upper bound always bound the actual pattern contrast. And how do we do this? So basically, we have a reaction diffusion system. We have some diffusion term and some reaction term. So this is a mass conserving reaction diffusion system, and this reaction part will lead to some reactive look lines, which is the stationary state of solution of the reaction itself, so that we can draw the reactive look lines in the system, and the thermodynamics will set some bound on the reactive look lines. So we have upper bound and lower bound. So that means these look lines will be inside the space. And if it's a mass conserving system, it has been shown that there is a conservation law in system that the weighted average of the concentrations should be a constant, which determines the flux balance subspace. And also it has been shown in some previous paper that the intersection between the flux balance subspace and this reactive look lines will give you the minimal and the maximum concentration of the pattern. But this minimum and maximum concentration pattern should be upper bounded by the intersection of the flux balance subspace, and these two boundaries. We have these two blue dots, so which get the upper and lower bound of the concentrations. And if we consider it's kind of a simple two-level system, like we have seen one spontaneous reaction and one driven reaction, so we will get the thermodynamic bound of the concentrations, which is determined by the drawing force you provided to the system. And we can see some patterns and two limiting cases determined by two different pathways. And by simply rearrange this expression, we get a bound on contrast. And we can numerically verify it on this kind of one-dimensional system with smaller driving force, we have a small range of pattern. With a larger driving force, we have a larger range of concentrations. And the upper bound always set some constraints on the contrast of the pattern. So that means we have the quite general framework for chemical reaction system as long as it is defined in a thermodynamic consistent way, and we can apply it to different biological functions. There are some few examples I studied in our paper, but also there are a lot of kind of other examples can be studied using this approach. So to a summary, so when system has thermodynamic equilibrium, so we only have a single solution, which is the Boltzmann distribution. And when we have some driving force, we can expand a solution space. And then the exact solution can move inside the space by tuning the kinetics. And so that we can lower down the error rate by kinetic proofreading. And if we further increasing the driving force, we will have a larger space. And in larger space, we have more freedom to design the dynamics of the system. In larger space, we can, for example, we can have some multiple stationary states. We can have some multi-stability. Also, we can describe, for example, the chiral symmetry breaking in molecular network. Finally, thanks to my supervisors, Daniel and Paulo. And if you are interested in the technical details, you can find these two papers.